So hi, my name is Uri, and this is Dan. We're both with Gigaspaces. I run the product team. Dan is one of our lead developers. Um, and basically what we want to do in this kind of exercise is to go through the evolving world of orchestration tools. So essentially kind of do kind of a rundown of all these tools and get the goods and bads out of each of these tools. So we're going to start with kind of talking a little bit about what orchestration is and what approaches exist to it. Then a little bit about our method of comparison, what we did in order to do this roundup. We're going to talk about individual tools, although we're not going to get into much of the details, just like highlights of what each tool does and how it works. And then some summary words around how we can combine some of the tools and what you basically think people should do when they face this problem of what tool to choose. So when we talk about common characteristics of those tools, most of them use some sort of DSL, like a blueprinting language to describe stacks and topologies. If you know Heat, we have the Heat orchestration template. If you know CloudFormation, then they have their own format, and Tosca is one of them. So it's kind of the same approach here. Based on this blueprint, they usually take and analyze the dependency graph and then execute some specific set of steps in order to execute to materialize the blueprint. And one thing that most of them do is actually pass contextual information from one part of the blueprint to another. For example, if they create a VM or a network and then they need to attach a VM into it, they actually pass the ID of that network into the VM so it can be used by the orchestration tool to attach the VM to the network. Now, there are a lot of assumptions based on what you're going to orchestrate and where you're going to do that that will have significant effect on what the tool is going to look like. So we kind of categorize the world into three pieces, three types of orchestrators, if you will. Up at the top, we have what we call infrastructure-centric, basically focus on one specific infrastructure as a service and catering to that. Heat is a good example for that. CloudFormation is another example. There are tools that are container-centric, mostly around Docker. We examined two of them, Kubernetes and Swarm. There are a few more, but these basically assume that all of your workloads are really container-based. And there are no non-containerized workloads. If there are any of these non-containerized workloads, they're actually handled outside of the orchestrator. And then we kind of did a take on the Mirantis pure play OpenStack piece, and we call it pure play orchestration. So these are tools that are not tied to a specific infrastructure or a specific workload. And they try to be more of a generic orchestration tool. The way we did the comparison is we took a pretty simple application, not that simple, but pretty simple, and tried to kind of characterize what it would take to set it up, to tear it down, to manage it or scale it, or to recover it from failures, and basically cater for the entire life cycle of that application. We did try to make it as real life as possible in the sense that we're not going to take just one web server and one database. It's really clustered and has a load balancer and these kinds of things. And along these three groups, we chose those tools. We choose Kubernetes and Docker for the container-centric orchestrators. We choose Tosca/Cloudify and Terraform for the what we call pure play, and we chose Heat for the infrastructure-centric. Obviously, there are a lot more tools and approaches out there, right? So there's the whole config management tools, which at least the modern ones like Ansible and Salt kind of overlap a little bit with some of these tools. There are PaaS platforms, but we intentionally kind of chose to only focus on these five because there were only three of us and we didn't have enough time to do that. So this is the test application, just a short walkthrough of what it does look like. So it's a simple web app, basically containing a load balancer. We try to use LBAS, Neutron LBAS for that. Basically three web servers, stateless web servers that connect to a Mongo cluster. So we put the Mongo S service in each of those VMs. Basically, we have three VMs here. Down at the bottom, we have three Mongo shards. Each shard is a replica set on its own. And up on the right-hand side, we have the Mongo config servers. So anyone that's ever done like Mongo clustering, this should be pretty familiar to you. Note that there's also, as part of the orchestration process, we're not just creating VMs. Okay, better? Much better, okay. Note that as part of the orchestration process, we're not just orchestrating VMs. Actually, yes, it's easier. We're also orchestrating the infrastructure pieces, right? So you see networks here, and those kind of shields actually symbolize security groups. So it's not just about orchestrating the software components, but a lot of the infrastructure. There are a number of steps here to basically orchestrate all of this thing. So I'm just going to kind of whiz through them. So the first thing we need to do is actually create the infrastructure. Already here, we need to do some sort of orchestrations because we can create the network, the VMs before we create the networks. We can create the VMs before we create the security groups. So you already need to do some sort of dependency analysis and set up some things before the others. Then you need to install the software. Usually, if you're using Docker, you just download the images. If you're using other tools, you can run Chef or Puppet or Salt or Ansible to configure the VMs. Then you start orchestrating the startup. You cannot do it all at once. You just can't start all the processes all at once. You need to do it in a specific order because the order does matter here. So for example, in the case of Mongo, for each replica set, you first need to designate a master. Then once you need to start the replicas and notify them where the master resides. Then you need to start the Mongo config servers and basically point the Mongo S servers into the Mongo config servers and basically initialize the shards one by one. Basically add the shards into the config servers configuration using one of the Mongo S's. So this is quite an involved process already. Then we basically need to initialize the data in the MongoDB database if we haven't already. Start the Node.js processes and basically introduce them into the load balancer. Right? So we have 10 steps. This is just a setup. If you think about other processes like tear down or like scaling or healing or these kinds of things, or updating the code, these are already separate processes that each one of them can take even more steps than what I described here. So again, we have it's not just about setup. It's about a lot of other orchestration processes that you need to cater for. So that kind of represents a few common requirements. The first one is the need to be able to manage dependencies. So you have a certain blueprint or an orchestration plan. You need to identify a dependency graph that actually will allow you to understand which components, which parts of the plan you need to create before other parts, and also pass information from one part of the graph to the other. The process needs to be obviously reproducible, so you need to be able to run the same plan, the same blueprint over and over again and get the same end result. You don't want to get different end results on every run. It needs to be clonable, so that means that you actually should be able to create multiple replicas of the same plan on your environment. So one plan should not interfere with another. That will help you, for example, to build a test environment and a QA environment and a production environment all side by side with one another. And it needs to be recoverable. Recoverable means that if something breaks in the middle of the orchestration process, there needs to be some clear way to clean up the environment and start all over again, so you get the end result eventually. If that's not the case, you're in a very big problem. So we'll start with a comparison, and first we're going to do the container-centric orchestrators. So I'll let Dan walk you through that.
Hi. So, yeah. Okay. So we'll be speaking about these two tools. I'll start with Swarm. So Swarm, it's written by Docker. That's a native clustering system. So basically what you have like a pool of hosts. All of them have a Docker daemon installed on them. And from the client perspective, you use it as if you were using a single Docker daemon. So we'll go into the details, but we'll see. So from the user's point of view, if you know how to use Docker, you just Docker run, pretty similar. Architecture-wise, so you have the manager. As I said, the client speaks to this manager, and the manager delegates the scheduling of the containers to the different daemons. Yeah. Okay, so as we said, we'll just see like a highlight of a solution of what we just described. You can see here, let's say we want to deploy the replica set, the replica sets of MongoDB. So we'll say for each replica set instance, we'll run this command here. And the things to note that are relevant to Swarm as compared to Docker alone, you see we say affinity and we say constraint. So this is the feature that, the major feature that is provided. You say, I want to place this, like for each replica set instance, do not place it near other replica set instances, do not place it near other config servers. Or for instance, you want to say, do place it on the daemon labeled MongoDB because the image is already there, and so it'll get deployed faster. Thing is, after we do that, that's a pretty manual step. We still need to somehow like SSH into the machine or Docker exec or whatever to run the initialization code of the replica set. So orchestration-wise, it's pretty low level. It's like you just do these things. Pretty similar. This is how you would, for instance, deploy the Node.js. One thing to note here, you say we still inject the IPs of the Mongo config servers, of the Mongo routers. Sorry, that's something that is not provided out of the box. You need to somehow do Docker inspect to get the IPs and use that. Yeah, there's nothing much to say about this one. Scaling out, it very much depends on the application, but there's nothing very specific. Like if you have like the automation to do the deployment for you, so scaling in and out should be pretty, like scaling in is very easy, scaling out should be pretty straightforward, you just execute the same scripts. Yeah, I hope it was like enough. Nice thing about Swarm, about using it, is that it's like you don't have to learn anything new if you know how to use Docker and if you know how to deploy the application. You just model these same steps in containers and you just execute in the correct order. The placement affinity, we didn't stress it high enough, but it's pretty easy to achieve high availability with this feature. It's very declarative. You don't have to think about where your replica set instances will be deployed. We said nothing about setting up like this cluster itself. That's because it's not handled. You can use tools like Magnum, that just came out, or I don't know, a Docker machine can set up on different cloud infrastructures. Everything's pretty manual. And also, all these different aspects that we didn't address at all, that are like monitoring, healing, scaling, are something that you should use other tools to address. So this was a highlight, like a high-level view of how a solution may look like. Moving on to Kubernetes. So this is a container cluster manager. This one's by Google. We'll go over these few different aspects, like words, whatever. So you have pods. Pods are like they're a tightly coupled group of containers. What that basically means is you have, for instance, you might have a Node.js instance application and a MongoDB router running in the same pod. So they share the same namespace in terms of networking, so they speak with each other through localhost. They share volume, so they can have the same file system access, etc. Replication controller is how you would keep a pod running. This is how you would say, I want a replication controller, I want to have, I don't know, 3 instances, And at all times, Kubernetes will take care of like moving things around. If things break down, it would make sure these are alive. Networking-wise, we mentioned that each pod gets its own speaks internally using localhost. So between the pods, each pod gets its own IP address. And service is what you would do to have like a load-balanced endpoint through a set of pods. We'll see a specific example. Architecture is pretty similar to what we saw with Swarm in terms of you have the manager and you have the minions. Client speaks with the manager. It's nothing much to say about it. Just skim through this. This is like how a replication control configuration would look like. You say, I want 5 replicas of this. And in this case, we have a pod that runs a replica set instance and some administration node alongside it that may add and remove members from the set as they get added and removed. Similarly, this is how you would specify a service. So in this case, we say we want the Node.js pods to be serviced by a single endpoint. Say this service gets an IP address. On each request to port 80, it'll get delegated to one of the pods on port 8080. Like, all you do is specify this, and it just gets configured by Kubernetes. So yeah, deployment. So we won't go into the files themselves, but say we model the application. We have like a bunch of files that look similar to what we just saw. So once again, in the correct order, we'll just do, okay, I want to create a replication controller for the 3 configuration servers, and then I want to create a service for them because I want them to have a static IP address that can be addressed at all times by the Node.js, by the Mongo routers. Similarly, we'll do the same thing for the Mongo S router. I don't know. Nothing like this starts to repeat itself. Okay, what else? Okay, healing-wise, it's an interesting feature. Like the replication controller, it's pretty. If your application like can withstand, like it's like can start and stop it at will. You just wrapping a pod with a replication controller makes it very easy. Like Kubernetes takes care of everything. If some host that like falls down, the manager will move it around to some other live host. Continuous deployment-wise, it's another pretty easy feature. You just, if you want to say upload a new version of your Node.js application, you just you sort of start with a new replication controller that has 0 instances, and you shift the balance. And if something breaks down in the middle, you can just say, okay, I just forget about this new version. I want to roll back to the old one. Yeah. Okay, so as we said, for auto healing and load balancing, it's a pretty simple configuration. We didn't do much to handle that. Scaling as well, it's if your application can handle it, you just increase the number of instances and it just works. On the opposite side, I know it's like somewhat, you can specify the host that you want your pods to get placed on, but it's not as declarative as we saw with Docker Swarm. And to the last point, again, it's like modeling of a stateful application in Kubernetes is somewhat not as dynamic. You need to, you need to see the application itself. If any one of you will go into the link that we just provided, there are files to see that. Yeah, so,
Okay, so I got 10 more minutes before Florian kicks me off stage. All right, so I'll kind of run through this. The next set of tools is what we call pure play orchestration. We start with Terraform. A few words about that. It's a very simple command line tool. by HashiCorp, simple in a good way. You just download it. It's a Go application, so basically you just download, unzip, and run it. It has a notion of resources. Basically, these are things you create on your IaaS environments. There are providers that implement the creation of resources, and provisioners. If you're familiar with Vagrant, these are things that work on a resource after it's created. Has nice support for modules, basically ability to modularize pieces of your blueprint and tie them together in a way that's reusable. It has variables and outputs. If you ever used Heat, it's kind of like inputs and outputs in Heat or in Tosca. So I'm going to run through the configuration. Just a few words about the way Terraform works. Our solution is we chose to have one top-level configuration file, which creates basically everything. It has very nice support for OpenStack. There's quite a robust provider for OpenStack. We did choose to use a module for the MongoDB shard. So we're basically specifying each shard as an import of that module. There's no easy way in Terraform to say I want 3 pieces of that module. So I basically have to copy and paste them for each additional copy I want within the file, which is kind of non-elegant. The other bit is that it's not so easy to do what we call kind of cluster initialization steps, and in the Mongo case, it's steps that are, I call them not symmetrical, right? You need to pick one of the instances and then run a certain script on it, or basically work on just one of the Mongo servers and add the shards one by one. So there are a few strategies to do that with Terraform. None of them are within the tool. They would probably require you to use either external scripts or additional tools, for example, Consul, which is another nice tool by HashiCorp that does cluster-wide orchestration. So you can see all the blueprints and configurations in the link that I just showed in the beginning of the session. Just to summarize, in terms of Terraform, on the pro side, it's very neutral, so it works with a lot of clouds. They have nice support for OpenStack, Amazon, Google, Azure, and a few others. On the OpenStack side, it does have very solid support for most of the common OpenStack resources. We have simple and elegant syntax, and it does support incremental updates, and basically you can plan things and then execute them again and again and see, and only basically Terraform will know what the diff is and only execute that for you. On the con side, it's the configuration is not portable. It's kind of hard to model non-infrastructure components. Basically everything on top of the infrastructure, and everything is done in the context of a single resource instance, so it's hard to do non-symmetric operations. So we'll jump to Tosca. So Tosca is a standard that's being developed by Oasis. Standard is a body that brought us AMQP and XML and a bunch of others. It's basically a meta language, so you can define specific types in it and compose them together into a blueprint. Cloudify is an implementation of Tosca, which basically takes this meta language and implements it with plugins and provides also not just the setup or installation processes, but also post-deployment aspects of the way you would do things, basically by using common open source tools like Elasticsearch and the Elk Stack and InfluxDB for metrics, and Riemann for policies, and a few others. So with Tosca, the way we modeled it is we're having 2 separate Tosca blueprints that point to one another. Tosca has a way of substituting one piece in one blueprint with another complete blueprint. So we can specify, for example, in one place that this is a database, and then replace it. This is just kind of an abstract declaration, and then replace it with a complete new blueprint. The strong thing about Tosca is that it might not be suitable for small applications, but it has a notion of abstract declarations. So you can actually swap the implementation at runtime. You can say, for example, this is the Mongo database, and in your test environment, that can be just a single server. In your production environment, that can be replaced by a separate blueprint that models a complete Mongo cluster. So I'm skipping, again, all of the code here. Just another comment about things that are handled by Tosca and Cloudify. It does also take further step into dealing with scaling and monitoring and policies. So that's something that's not typically modeled by other orchestration tools. So that allows you to kind of cater for requirements that are not just part of the, I would say, part of the original orchestration process. On the pro side, it's infrastructure and framework neutral. So you can model any kind of application, any kind of cloud with Tosca. It has a complete lifecycle management, right? So it's not just about setup and teardown. It models both the application and the software, so it's kind of very natural to model not just the infrastructure, but also what's installed on top of it. On the con side, spec is still evolving. Even Cloudify, it's kind of, we consider the flagship implementation of that. It's not 100% compliant. And right now, there's a limited set of tools. Which brings me to Heat, to kind of finalize this thing. Anyone here using Heat in practice? Except for Florian. All right, great. Good. So Heat is a templating engine and basically a CloudFormation equivalent for OpenStack. In terms of architecture, I think most of you are familiar with it. There's an API layer, then there's an engine. The engine knows to speak with the respective OpenStack components and provision the resources. We modeled the blueprint using a Heat orchestration template, kind of a YAML file, kind of similar to Tosca actually. The solution here, we actually modeled 3 different stacks and composed them. Heat allows you to do stack composition in quite an elegant way. So we basically modeled the front end on one side here, the Mongo config servers on the other side, and then all the Mongo replicas in the third blueprint, and tie them together using stack composition. So you can see all the details in the slide deck. On the pro side, Heat is very good because it's native to OpenStack. If you're an OpenStack user and that's all you're going to use, that's probably the way you should go. There's built-in mapping for all of the OpenStack resources, so you're not going to get caught behind with some new Neutron functionality that's not including the orchestrator. Heat is probably going to cover that faster than anyone else. On the con side, it's only applicable to OpenStack. It's mainly focused on infrastructure and not software configuration, so it's hard to do those non-symmetrical configuration steps that I mentioned. And it doesn't deal with anything beyond setup and teardown. All right, so just to wrap up, obviously this was a very short rundown of all the tools. Naturally, you don't have to use the tools exclusively. You can actually combine them together, right? So we've seen some of that in the recent summit. So you can set up Kubernetes and Docker on top of OpenStack using Magnum, which is a new tool, and then basically use this for part of your workloads, and then use Tosca or Heat for dealing with the non-containerized workloads. So there's a lot of room here to mix and match between the tools. I'm going to end with a few final words that I think Nati very much likes to quote, is that the only thing that's constant is change, right? So we're talking about Docker today, which is kind of very, very popular, and there are a lot of tools around that, and a lot of people are talking about that. If we're going to sit here in about 1 or 2 years from now, I'm probably going to talk about something else. So the thing you need to keep in mind is basically not get tied to any specific implementation or specific type of technology that will lock you in to those tools. You need to build your solution in such a way that they're going to be adaptable to all the changes that are going to come. And with that, I'm running out of time. I'm here throughout the day in the Gigaspaces booth if you want to ask more questions about this. I know it was very short. So thanks for listening.